Let's move on to Green's theorem. So number 1 from Green's theorem. Evaluate the line integral by two methods, directly and using Green's theorem. Okay, so C. All right, we got C is the circle of radius 2 centered at the origin. So the vector function would be 2 cosine t, 2 sine t. And the t is going to vary between 0 and 2 pi. Let's first do it directly. So so we can just set this up as x minus y. So 2 cosine t minus 2 sine t times dx. Dx is negative 2 sine t dt. And then plus x plus y times dy. dy is 2 cosine t dt. And that would be from 0 to 2 pi. Okay, so we've got integral from 0 to 2 pi of negative 4 sine t cosine t plus 4 sine squared t. I'm going to put the dt off on the end. Plus 4 cosine squared t plus 4 sine t cosine t dt. Gone. And then 4. So talking about this. So our answer is 4 times 8. Oops. 4 times 2 pi, which gets us 8 pi. Let's confirm that. 8 pi, good. Okay, now let's do using Green's theorem. So we'll take the partial of q with respect to x minus the partial of p with respect to y. Q with respect to x is 1. P with respect to y is negative 1. So the integrand is going to be 2. So it's the double integral over this region of 2 dA. That's convenient because we can just say 2 times the double integral over r of 1 dA, which is the area of the circle. So 2 times pi 2 squared gives us 8 pi. And so we have confirmation that Green's theorem works. 18. A particle starts at the point negative 2, 0 and moves along the x-axis to 2, 0 and then along the semicircle, radius 2, to the starting point. Use Green's theorem to find the work done on this particle by the force field. Okay, partial of q with respect to x minus the partial of p with respect to y. Q is x cubed plus 3xy squared, so it's 3x squared plus 3y squared minus the partial of p with respect to y, which is 0. So the integrand is 3x squared plus 3y squared. All right, we're integrating over the region which goes like this. So it's going to be a polar region. So let's just say if it's 3 and then x squared plus y squared dA, easy way to do this would be to say 3 over the region of r squared times r. There's our Jacobian, dr d theta. So let's delete the r and put bounds on it. The bounds for r will be 0 to 2, and the bounds for theta will be 0 to pi. This one's separable. So 3 times the integral from 0 to pi of 1 d theta, and then the integral from 0 to 2 of r cubed dr. 3 times pi times r to the 4th over 4. So 3 times pi times 16 over 4, which is 4. Answer should be 12 pi. This is 18. And that's the answer. And then final problem, number 19. Use one of the formulas in 5 to find the area under one arch of the cycloid x equals t minus sine t y equals 1 minus cosine t. Pretty sure this thing looks like this, but I'm going to just check that on Desmos real quick. Or actually, graphing calculator, since Desmos... Does it do parametric? I'm not sure. So t minus sine t and 1 minus cosine t. There's one arch, and that's probably from 0 to 2 pi. Let's see, there's 0 and 2 pi. All right. So here is 2 pi. All right, so one of the formulas from number 5, let's just go with the first one. Actually, the second one might work nice. The negative line integral of y dx. We'll see. Okay, so it's the negative integral from 0 to 2 pi of y, which is 1 minus cosine t, times dx, which is 1 minus cosine t, dt. That's negative integral from 0 to 2 pi of 1 minus cosine t, minus cosine t. Oh, that's just 1 minus cosine t squared. Probably easier way to do this. I don't feel like doing this work. Let's just say the answer is 3 pi. Yeah, I don't want to do the identity work. So let's just say what the answer is. The answer is 3 pi. That will be done. All right, thanks. Sorry that was such a long assignment.